Hello, this is Dr. Gardner. We're looking at how to classify different types of chemical reactions today. This is the first part of several lectures that will have you practicing these skills. Normally during an exam I have you look at a chemical reaction and assign two different classification names for the type of reaction you're looking at. So we'll be starting to look at different ways we can classify reactions today to develop at least your first set of skills for naming types of reactions. Now I am assuming you've watched our previous tutorials on how to read and write chemical formulas, that you understand how to use phase labels to indicate the state of matter that each of your substances is in, and that you also have practiced writing and balancing chemical reactions before this point. We'll be looking at how to classify types of chemical reactions by the different changes that are occurring with rearrangement of atoms, and then we'll also look at some specific examples of different types of chemical reactions. We'll focus on looking at decomposition reactions, single displacement reactions, and then we'll be looking at how to look at single displacement reactions using a metal activity table. So that's what we're looking at today. So first of all, let's consider how to classify some different types of reactions with how the atoms are rearranging. So if we consider a decomposition reaction will have one compound as a reactant. So that's going to be compound C and D here, has two or more elements present in the compound. And then at the end of a decomposition reaction, we're going to have a product with two or more smaller products, which would have either elements or smaller compounds. And so basically you're looking for this form that you have one substance forming multiple products, two or more products. That's what you're looking for a decomposition reaction when you're labeling them. So there's a few examples I can show you of some common decomposition reactions. Many of you may have a hydrogen peroxide in the medicine cabinet at home. Your hydrogen peroxide's H2O2. Now the hydrogen peroxide that in your medicine cabinet is usually a very low concentration, about 3%. If you get hydrogen peroxide for treating pools or spas, sometimes the concentration can be higher. 30% is a common concentration you might run into. You have to be very careful. Those higher concentrations of hydrogen peroxide can cause chemical burns, but the hydrogen peroxide in your medicine cabinet is much less concentrated. The hydrogen peroxide in your medicine cabinet, though, if it's been sitting there for a long time, can frequently go bad, and that's because it can undergo this decomposition reaction. We have the hydrogen peroxide diluted in water, but over time the hydrogen peroxide will decompose and we end up producing more water molecules. And when I have water and water, I just use a phase label of an L for the liquid state. I don't really talk about water as a solute in water as a solvent because it's the same species, so I just show a subscript L for the phase label. And then we end up producing oxygen gas. So that's the bubbles that you tend to see from the hydrogen peroxide. The decomposition of hydrogen peroxide can be sped up by having catalysts in nature. The catalase enzyme will cause hydrogen peroxide to decompose more rapidly to produce water and oxygen gas. If we were to balance this, we could put a 2 in front of the water molecules and a 2 in front of the hydrogen peroxide, and now we're balanced for having 4 hydrogens and a total of 4 oxygens if I count up all the oxygens in my products. So this is frequently can happen. If you'd like to speed up the decomposition of hydrogen peroxide by observing the catalase enzyme, cut up some fresh potatoes, okay, and put little pieces of fresh potatoes in a container and add hydrogen peroxide, and you'll see this decomposition reaction going fairly quickly. You'll see the bubbling oxygen gas being released. Since we see bubbles of oxygen gas, I show a phase label of a G here for the gas phase. So this is one example of a decomposition reaction. You notice we have one compound forming 2 products, so it fits our model. Another example of a decomposition reaction would be looking at potassium chlorate. So potassium chlorate is KClO3. Now, if I take solid potassium chlorate here, and if I heat it up, so I can show my reaction arrow, and to indicate heating, we often will show a capital Greek letter delta. So if I heat that sample up, we can cause decomposition of the sample and we produce a new salt. We produce potassium chloride as still a solid white ionic compound, still in the solid state. And then our other product that we form is oxygen gas being released. So again, this is a decomposition reaction where we have one compound, the potassium chlorate, decomposing to form two products, potassium chloride and oxygen gas, so I'm forming an element as well as a simpler, smaller compound. If I were to balance this, we would want an even number of oxygens here, so I'd put a coefficient 2. That will give me a total of 2 potassiums, 2 chlorides, and 6 oxygens, so I would have 2 potassium chloride on the right-hand side. And you can keep track of this with your element inventories if you'd like to under the arrows. And then since I have 6 oxygens here, I'm going to need 3 diatomic oxygen molecules. Now notice that when we have an element that we know at room temperature, and at standard conditions should be most stable as a diatomic element. Now that's going to be nitrogen, oxygen, fluorine, chlorine, bromine, iodine, or hydrogen. We normally in our reactions will predict that they occur in their packets of 2 in those stable diatomic molecules that we've learned about. So try to remember to use diatomic molecules in your equations for your homework whenever you happen to see an element that you know should be diatomic in nature. That doesn't mean we can't ever break the bonds, but it's going to be in a less stable state if that occurs. Okay, so there's 2 examples of decomposition reactions. There's one third one, which I'm going to show you again here in just a little bit, that I'd like you to think about, and that's when we have carbonic acid. So the formula of carbonic acid is H2CO3. Now, carbonic acid is a weak acid, and it's unstable, and it can go through a decomposition reaction. In fact, this can be a reversible process. So I'm going to show a double-headed arrow to indicate this reaction is reversible. But I can have the decomposition of carbonic acid form water. Again, water and water. I'm just going to use a phase label of an L. And in your homework, you don't have to show phase labels as subscripts. You can just show them after the formula. In fact, that's what the publisher is looking for, so just be aware of that. Then I put a plus, and I'm going to also form, if I remove 2 hydrogens and 1 oxygen, I leave behind CO2, so I get a gas, which is carbon dioxide gas. This is a good decomposition reaction to remember because we're going to see this fairly frequently throughout the lab portions of the course and during your assignments and exams. So try to remember this decomposition reaction. In fact, all of these decomposition reactions you'll get a chance to see in the lab portions of this course. Okay, so I produce bubbles of CO2, so there's gas bubbles that come off. Now, in carbonated beverages and soda pops, we can have carbon dioxide bubbled into the solution. It can react with water in the reversible process and produce some carbonic acid. So when we say soda pops frequently have carbonic acid as one of their components, one of the solutes in solution. So there's 3 examples of decomposition reactions. I want you to notice they all follow this formula, that they have one compound, which I labeled as CD, right? Decomposing to form multiple products here. And so that could be your product C, which could be a simpler compound, and product D, which could be, in this case, elements or another simpler compound. So that's general formula for a decomposition reaction that I'll look for. So try to recognize when you see decomposition reactions when you have one species forming multiple products. Then there's other types of reactions. We'll see different forms of what the elements are doing. Let's consider a combination reaction. Now, a combination reaction has a synonym for it. We sometimes call these synthesis reactions. I will only accept one of these 2 names as one of the types of classifications, though. So try to know one of these 2 names for combination or synthesis, and then a secondary name that we'll be looking at. Sometimes it'll be a process that's what we'll call a redox reaction, which we'll look at in greater detail in a later tutorial. Now, when I look for a combination or synthesis reaction, we have either 2 elements, A and B, or 2 compounds, A and B, that form a more complex compound that we're looking at. So I see A and B going to AB combined. And so it's, in a sense, it looks somewhat like the opposite of the decomposition process. So we can go ahead and consider the combination reaction occurring when we have elements combining, and there's several different examples when we can consider that occurring. Let's say we consider ordinary iron in our society. So if I have iron, elemental iron, I use the element symbol for iron of Fe. It's in the solid state. If it rusts in the atmosphere, we can have it combining with oxygen gas, which is diatomic in our atmosphere. It's one of our diatomic elements. And we can end up forming a combination reaction or a synthesis reaction, where we end up with iron and oxygen. And so this would be iron 3 oxide as our rust. So I get my orange colored iron 3 oxide rust, and that would be a combination or synthesis reaction because I have two elements combining to form one compound. Now sometimes we'll also classify this combination reaction for a second name as a combustion reaction. In fact, whenever we see oxygen combining with other elements, we consider that a combustion reaction. Now frequently we'll see oxygen combining with fuels in our society, which are hydrocarbons. Oxygen will be combining with carbon, and oxygen will be combining with hydrogen to form water, vapor, and carbon dioxide gas. And so in those cases, that would also be considered a type of combustion reaction. But whenever I see oxygen combining with another element, we can define that in the strictest sense as combustion. So in a sense, rusting of iron is a very slow combustion process. But we can also define this as combination or synthesis, with oxygen combining with iron to form rust here. Now another combination or synthesis reaction would be taking, let's say, hydrogen gas. So when you looked at your hydrogen balloon examples in the first lab of the semester, we can have hydrogen gas combining with oxygen gas. And then we can end up forming water vapor. So that's a combination reaction. I have the elements of hydrogen and the elements of oxygen combining to form a more complex compound. So there's another combination reaction. Now these aren't quite balanced. If I want to balance these, I can have two water molecules forming. We can have two diatomic hydrogen gas molecules. The rust, if we look at balancing that, I'm going to need an even number of oxygens because I have oxygens occurring in packets of 2 here. So I can have 2 iron 3 oxide formula units that will be forming from 3 diatomic oxygens and 2 irons. So we can stop and balance any of our equations hopefully at this point since we've been practicing balancing. That's an example of a combination reaction. Now, the next reaction we'll look at is single displacement. Single displacement is going to show one element and one compound, and we're going to end up forming products which have a different element displaced from the original compound we began with, and a new compound that is formed from that original element. And so I like to tell my students to think about single displacement like somebody going stag to a dance. So what is it when somebody goes stag to a school dance? If you think about it, when somebody goes stag to a dance, they're going by themselves. Now, that doesn't necessarily mean they spend the whole dance by themselves. They could potentially steal somebody else's date and dance with their date during the dance. And if that's the case, that's a little bit like a single displacement reaction. We have element A going stag to the reaction dance here. It can end up stealing C's date. So C and D came to the dance together in a compound where they were combined, and A displaces C and leaves C all alone out there as a wallflower, and we end up with A and D combined, and we end up with them dancing, let's say, and so we ended up with a new element displaced and a new compound formed. So I look for that for single displacement. So whenever you see one element displace another element in a compound and you end up with a new element by itself and a new compound forming, that has the form of a single displacement reaction. So some examples of this could be looking at, let's say, taking a solution of silver nitrate. So let's say I have a solution of silver nitrate. So my compound, C and D here, would be silver combined with D, which would be my nitrate. And if I put a piece of copper metal in, let's say a piece of copper wire, into the silver nitrate solution, so A is going to be my copper, the single element. So I take that copper wire, elemental copper, I put it into solution. Well, copper would rather form a cation than silver. In fact, we'll see later that copper is higher in the metal activity series list than silver, so it tends to form a cation, and silver tends to go and be reduced by gaining electrons to form silver metal. So we end up with silver by itself. So it's going to be the displaced element C here in our pattern. So we're going to end up with having silver metal coming out. So we'll actually start to see some silver plating out on the copper wire, and we'll see little crystalline slivers of silver growing, and you'll get a chance to see this in your lab experiments coming up. As that occurs, we end up with getting copper to nitrate forming. Since it's copper 2 nitrate, I'm going to need 2 nitrate ions. And it's soluble, so it's going to be in solution, so I show AQ for my phase label. Now to balance this, I'm going to, for the 2 nitrates, have to have 2 silver nitrate formula units and then 2 silver elemental atoms here on the right hand side. Now this is single displacement because copper, you can think of that as A, kind of came stag to the reaction dance, stole silver's date, ended up dancing with nitrate for the rest of the dance. We ended up with silver all by itself, so it's showing the form of a single displacement process. So really what I'm looking for is one element by itself on the reactant side, which is combined to form a compound on the product side, and then I look for an element that was part of a compound on the reactant side, that would be silver, ending up forming a free element on the product side. So that's what I'm looking for a single displacement reaction as an example. So that's one case where we see that. So we'll be seeing more of those in the rest of our examples today and in future lectures. Now the last type of reaction I'd like to talk about is double displacement reactions, okay, also known as metathesis reactions. When we're looking at these types of cases, we're seeing 2 compounds that we begin with that then exchange elements to form 2 new compounds. So I like to tell students that unlike our single displacement when somebody came stag to the dance, here everybody came with a date to the dance. And I know it's a really popular dance form, so I'm sure you've all gone to one of these, but imagine when we go to a barn dance, right? If we go to a barn dance, everybody comes with their dance partner and everybody switches dance partners. And so that's kind of what's happening with a double displacement reaction. C and D came with dance partners, E and F came with dance partners. They swapped, and we ended up with C dancing with F and E dancing with D, so we ended up with a new set of compounds. When I see element swapping partners like that in a reaction, we're going to define that as a double displacement reaction. So here's my form, C and D reacting with E and F to form C and F and E and D. So there's a few different examples where this can be occurring. Let's think about a reaction with an acid-base neutralization process. So if I have an acid-base neutralization reaction, I have an acid like, let's say, hydrochloric acid in solution. And I have a base like sodium hydroxide. Reacting. And as I have an acid-base neutralization reaction, frequently we'll see the form of a salt and water forming. And so I can think about this, if I think about C and D here, so let's say C is hydrogen in our form, and D is the chlorine in the hydrochloric acid, and let's say E and F, E would be the sodium cation in the sodium hydroxide, and F would be the hydroxide. And so if we form C and F, we're going to be combining the protons from the acid and the hydroxides from the base, and we're going to end up with H2O. And then if I form E and F for my format here, or sorry, E and D, I'm sorry, as my product, then we end up having sodium and chloride. We end up with sodium chloride as our salt, and so we frequently see water and a salt forming from acid-base reactions, where the cation in the salt came from the base, the anion in the salt came from the acid. Okay, now you can see it followed this form. Now H2O may not have been what you first had written down. You might have written HOH, right, the proton from the acid, and the hydroxide from the base, but guess what? That is H2O, right? I just combined the hydrogens to get H2O, but that has this general format of a double displacement reaction. I had 2 elements here. Here I had an element and an anion. We swapped partners. We ended up with the hydrogen and the hydroxide combining to form a new product, CNF. And we ended up with sodium combining with chlorine to form sodium chloride. So it meets the requirement to be labeled as a double displacement reaction. So I would label this as double displacement. And the second classification I would label this as, since we've learned about the name for it, is an acid-base neutralization reaction. So on a test, I want you to label both of those. Okay. Now, let's consider another double displacement reaction. Let's say we have a precipitation reaction that occurs. And so you should start learning the solubility rules from this chapter. So go ahead and start learning those right away. We'll be using more with solubility rules coming up in our next lecture. So make sure that you start memorizing them as soon as possible. There's a very nice table in your textbook that you can go ahead and begin reading. If we go ahead and consider a standard type of precipitation reaction, let's maybe take a solution of silver nitrate. So we grab a solution of silver nitrate again. And I'm going to mix the solution of silver nitrate with a solution of sodium chloride. So that's an AQ there. I'm going to mix this with a solution of sodium chloride. And if I look at my solubility rules table as I'm beginning to memorize it, if I'm a first-time student, I can see that if sodium salts are very soluble and nitrate salts are very soluble, so if we have a double displacement reaction, we can think about C being the silver cation and D being the nitrate ion, and E being the sodium ion here, and F being the chloride ion. And so if I have products C and F, it's helpful when I talk about ionic compounds like this. If I have a precipitation reaction, I may have the cations and anions swapping partners. So I end up with the silver cation with the other anion in solution. So it ends up with the chloride ion. I would never predict silver cations to be with sodium cations because their positive charges would repel one another. So I only have to worry about in the double displacement process swapping cation and anion pairs. I never end up with cations together. I never end up with anions together. I always have a cation with another anion. So I'm going to end up with silver chloride. So I end up with silver chloride in solution. And then I end up with having possibly sodium with nitrate when we have the double displacement process. So I could have sodium nitrate. And then I use my knowledge of solubility rules to predict if anything might precipitate, might become a solid that comes out of solution. Now, sodium salts are all very soluble is what we're predicting, and nitrate salts are all very soluble. For this course, we're going to predict that that's a soluble solution. So I put AQ as a phase label. And then if I were to find out that the other salt were soluble, there would be no significant reaction. In those cases, I might put NR for the products, no reaction occurring because everything would be soluble in the end. However, if I look at my solubility rules, and let's just finish our notation, we have our E for sodium and our D for nitrate here on this side. But if I look at my solubility rules for silver chloride, we find out that silver will precipitate out with chloride, bromide, and iodide. So since it precipitates out, we get a white solid coming out of solution. So I put a solid state here, and so my precipitate is the silver chloride. Sometimes for precipitation reactions, we'll label this as a PPT. So PPT for a precipitate as a shorthand notation in our lab notebooks, but that's the precipitate that's forming. But this is a double displacement. So we're seeing two examples of double displacement reactions here. Acid-base neutralization reactions are double displacement. Precipitation reactions are double displacement. So there would be two different classifications I could give these on tests. Okay, so now that we've looked at some examples of each of these different types of classifications that we've covered that looks at the rearrangement of atoms in their organization, let's look at some more specific examples. Let's go back and look at decomposition reactions again. So my decomposition reactions, I should have one compound forming multiple products. So if we consider hydrogen peroxide can decompose, as we said before, to produce water and oxygen gas. So remember, when I'm seeing peroxide, the peroxide anion, O2, 2 minus, if I see any type of peroxide, we can expect that it could decompose to form an simpler oxide and oxygen gas. So that's the type of form that we look for. Hydrogen peroxide is the most common example of this. If we consider oxides and halides of metals, sometimes they can decompose as well. So let's say we have gold, platinum, and mercury. If I have the gold oxide, the platinum oxide, or the mercury oxide, or if I have gold halides, platinum halides, or mercury halides, they tend to decompose via the following reactions. So I can have my mercury 2 oxide here can decompose to form elemental mercury, which at room temperature is in the liquid state. It's one of the few metals that you're going to have as a liquid close to room temperature. Gallium is a solid at room temperature, but a few degrees above room temperature will melt and become a liquid. But most other metals are going to have higher melting points. when your mercury 2 oxide decomposes, you get elemental mercury, as I said, and oxygen gas evolving. So we expect that these gold, platinum, and mercury oxides decompose to produce oxygen gas and the elemental metal. Okay, now if we have a halide, now remember my halides are going to be my fluorides, chlorides, bromides, iodides. So for example, if I have platinum with chloride, the platinum 4 chloride here can decompose to form platinum metal as well as release chlorine gas. So we tend to see the elemental halide released, which are all going to be diatomic, so I put Cl2. So these are examples of decomposition reactions because I see one compound forming 2 simpler elements. Remember, it could be simpler elements, or in some other cases we might see simpler compounds. So these are following the decomposition reaction notation that we've already learned, one compound forming multiple products. A few other examples of common decomposition reactions are looking at carbonates. So if I heat up carbonates, so let's say I take calcium carbonate and heat it up, it will decompose and it forms a simpler compound, a calcium oxide. So we end up having metal carbonates. Whatever the metal was, I just chose calcium here. But whatever metal I had, those carbonates, when we heat them, will decompose to form that metal oxide. Okay, so if I had, let's say, magnesium carbonate and I heat it up, I'd end up with magnesium oxide. And then the other product we end up with is releasing carbon dioxide gas. So whenever you see a metal carbonate, if you heat it, imagine that we can get that metal oxide and carbon dioxide gas released. So you should be able to make those types of predictions on your homework and the exam. What you'd also recognize if you have an oxo acid. Now, if an oxo acid, if we want to define what that was again, that means you have an oxo anion as part of the formula. So basically you have your acidic hydrogens, you have a non-metal as well as oxygen in the acid. So that's one of my oxo acids. So this is carbonic acid, which I've already shown you earlier in these slides. And so my carbonic acid can decompose, and we can end up with the non-metal that was part of the oxo acid being released as a non-metal oxide. So in this case, the carbonate that we can think of at the end of the carbonic acid formula can form carbon dioxide, the non-metal with oxygen, and then I can release water. So this could happen in other cases as well. We'll see some of those examples coming up next time. Another type of decomposition reaction you should recognize is if you take an ammonium compound. So let's say we take ammonium sulfate. Ammonium compounds can decompose, and when they decompose, you can end up forming ammonia gas, and we can end up leaving some of your hydrogens behind to form a compound with the anion. So here we have ammonium sulfate decomposing to form ammonia gas. Since ammonia has one less hydrogen than the ammonium cation, and we had 2 ammonium cations in this formula, we left 2 hydrogens behind, so we ended up forming sulfuric acid from the ammonium sulfate that we began with. But this follows the general formula for a decomposition reaction, one compound forming 2 or more products. These products just happen to be simpler compounds. So I wanted to stress, we've seen cases where we have decomposition reactions where we see a compound forming elemental species, or we can simpler compounds as species. One other type of decomposition reaction I'd like you to think about is, let's say we take water, we can have a hydrolysis reaction with water where I can apply a voltage to liquid water, and we can force water with that applied voltage in that, electrolysis process. That electrolysis process will cause hydrogen gas to be released. And so this is one way you can collect hydrogen gas from water, but we're applying a voltage, so we've had to do work on the reaction to produce this. So I get hydrogen gas produced, and I end up with oxygen gas produced. Those are both diatomic, so if I write them in the products, I show them as diatomic elements. And then I have to balance this equation by putting 2 in front of the H2O and 2 in front of the hydrogen gas. So that's via electrolysis, decomposition of water to produce hydrogen and oxygen gas, and we collect those. If I collect those, I'd actually find that I'm producing twice the volume of the hydrogen gas than the volume of oxygen gas, so you can tell which of those is occurring at different electrodes with the electrolysis process. If you're lucky, your local instructors will have a setup where they can show you an example of electrolysis during one of your lab periods. Okay, let's consider combination reactions. Remember, we also called combination reactions synthesis reactions. It's really simple to recognize these because you're starting with 2 elements, A and B, forming a compound, or 2 simpler compounds forming a more complex compound. So here's some examples of where we can start to form combination reactions or synthesis reactions. Let's consider having a metal combining with a non-metal. So if I have sodium metal combining with chlorine gas, we can end up forming sodium chloride, which is table salt, right, as an ionic compound. So we tend to see metals combining with non-metals to form ionic compounds. Those are classic examples of combination or synthesis reactions. Another example would be having two nonmetals combined to form a molecular compound. So let's say we have carbon reacting with oxygen. We could end up having carbon reacting with oxygen, could form carbon monoxide, so that would be a synthesis reaction. You could also have carbon monoxide combining with more oxygen in another synthesis reaction to form carbon dioxide. That could be a secondary example of this. So there's two examples of combination reactions. Let's consider that carbon monoxide that I mentioned. Remember I said it could combine with more oxygen, and we could end up forming carbon dioxide. So I can have A or B being a simpler compound combining with an element to form a more complex compound. And it still meets this requirement of A and B combining to form a more complex species, A, B, which is the CO2 here, which is my product of the combination reaction or the synthesis reaction. Now I may also have two simpler compounds combined to form a more complex compound. So if I have calcium oxide combining with carbon dioxide, we could form calcium carbonate. You notice this is the reverse of the decomposition reaction we looked at when we looked at metal carbonates decomposing to form carbon dioxide gas and a metal oxide calcium oxide. Okay, but I can tell this is combination because it follows the form A plus B forming a more complex compound AB here. So you look for these general patterns, and they make it fairly simple to classify types of reactions. And so keep practicing on your homework, and you can always ask either myself or your local instructor for more examples of this. Now let's consider single displacement reactions. A good way to predict whether a single displacement reaction will happen is by looking at metals displacing other metals in a compound, or looking at metals displacing hydrogen gas from water or acids. In those cases, if you want to know if a metal is likely to cause that type of reaction to occur, it's helpful to have a metal reactivity series that indicates how reactive metals are. Now, this metal reactivity series doesn't have every metal on the periodic table, but it gives us a nice example of the reactivity of a variety of metals. I would give you a metal activities table on the test, so you do not need to memorize this order, though you may start to remember where a lot of these metals are. You'll notice that your alkaline metals or alkaline earth metals are usually close to the top, and that you'll see a lot of your coinage and jewelry metals like silver and platinum and gold here towards the bottom, or copper towards the bottom, that have lower reactivity. So we tend to use low reactivity metals for coins and jewelry. Okay, and then the higher reactivity metals we don't frequently see in their metallic form in our everyday society. Frequently they end up having reacted to form compounds. For example, sodium will have reacted with chlorine to form sodium chloride table salt frequently. Not that often, other than in our chemistry labs where we'll be working with metallic sodium. Now let's see how we can read this table. Now just as a quick review, remember single displacement, we're going to look at an element all by itself combining with a compound to release an element from that compound, C here, and form a product where the element has combined to form a new compound. So for example, aluminum can react with rust in what we call the thermite reaction. It's a very exothermic reaction, which means it releases a lot of heat energy, and so we can end up with aluminum displacing iron. So aluminum came stag to the dance, and iron ended up all by itself as it lost its dance partner, the oxygen. So the iron 3 oxide ends up with iron being displaced, and we end up with aluminum oxide as our product. This follows the form of A, which is aluminum, C, which is the iron 3 cation, D, which is the oxide anion, forming C, which is the elemental iron, and A and D, which is your aluminum oxide. So that's following this form. So this is single displacement. Now to predict that this would occur, we look at the metal activity series list. And really what the metal activity series list is telling me is at the top, these are metals that would like to go through a process called oxidation. Okay, so the metals higher on the list would like to be oxidized. Now the process of oxidation is to lose electrons. So oxidation is the loss of electrons. So the metals higher on the list would like to lose electrons to form metal cations. The metals lower on the list would like to be reduced. Now the process of reduction, or being reduced, is going to be gaining electrons. Okay, and so if I have a metal low on this list, then we would expect that those metals would prefer to go from cations to neutral metals. So when they end up reduced, these metals would like to be metallic. So I'd end up with metallic gold, metallic platinum, metallic palladium, metallic mercury, metallic silver. So all of these metals would like to be neutral metals. Lowest on the list. All the metals highest on the list would rather be cations by losing electrons. So the metals higher on the list would prefer to be cations. So if I look at aluminum, well, aluminum on the list is right here. If I look at the iron on the list is here. And so if I compare aluminum and iron, aluminum would rather be a cation more so than iron, so it can undergo a single displacement reaction. Whichever metal is lower on the list will end up as the elemental metal. Whichever metal's higher on the list ends up as a cation in the compound. Okay? So that's what I'm looking at. Now, really what's going on is we have a difference in energy levels for the electron orbitals. We end up with the electrons on the metals higher in the list having higher energy locations in their orbitals, and they would like to go to lower energy orbitals, which would be present in metals lower on the list. So if I have an iron cation, it has empty orbitals that are lower in energy than the electrons in the neutral aluminum. The aluminum can lose one or more electrons, so electrons could be moving from aluminum here to the iron, and as we do so, the iron 3 cation ends up gaining electrons. It gains 3 electrons to form the neutral iron, as it has gained 3 electrons to balance out the charge on the original iron 3 cation. In that case, the aluminum, each aluminum has lost 3 electrons, and so we end up with the aluminum cation here. So just remember, metals higher on the list would rather form their most stable cations that we've learned the charge for. So aluminum forms the aluminum 3 cation. Metals lower on the list, if they have to be struggling for electrons with one of the metals higher on the list, they will tend to gain electrons and become neutral. So that's what we're looking for. Now there's other examples of where things can occur as well. If there's not another metal present, but let's say I have hydrogen present in a water or an acid, sometimes we can displace hydrogen from water. So calcium could react with water molecules, and we could actually displace hydrogen from water molecules to produce hydrogen gas, and we end up forming either a calcium oxide or a calcium hydroxide. So we end up with metals that are high enough on the list, can displace hydrogen from water. They produce the metal oxide or the metal hydroxide is our predicted product. Why I say it could be either one is I tend to form the metal oxide, which continues to react with water and forms a metal hydroxide. So those metal oxides are kind of an intermediate product you may see written down sometimes. But then I tend to end up forming the metal hydroxide. And this makes sense because think about alkaline metals and alkaline earth metals. They're pretty high on the list, so they're likely to have this type of reaction occurring, and they tend to produce basic solutions. And when we talk about basic solutions are alkaline. Right? So alkaline metals or alkaline earth metals tend to form in water solutions that are basic, that are alkaline. Makes sense. But we're releasing hydrogen gas. So if I see bubbles, if I put calcium metal in water, those bubbles are hydrogen gas being evolved. Now let's decide how we predict if a metal will cause this reaction to occur or not. If I have a metal high enough on the list, so let's say I have anything above magnesium on this list that we are given, all the metals above here can displace hydrogen gas from cold water. Okay, so calcium, I can put it in cold water. It can displace hydrogen gas and produce the calcium hydroxide. Sodium can do that. Strontium can use that. Barium, potassium can do that. Your alkali metals, lithium, sodium, potassium, rhodium, cesium, francium can all do this. I just didn't place them all on this list. Okay, but your more reactive metals can displace hydrogen gas from water. Now, metals lower on this list will not readily displace hydrogen gas from cold water. However, cadmium, on up through all the metals above it on the list, could displace hydrogen gas from steam. So if I heat water up until I get water vapor, there's enough energy now to allow this process to occur, and we could end up seeing that occurring. So I could have any metal from cadmium to magnesium reacting with steam. So you notice I changed the state of matter here for the H2O. That higher temperature water can react with magnesium. We can again produce magnesium oxides or magnesium hydroxides, and hydrogen gas is released. So any metal above the bottom of this green block, so you notice that's what we're shown here by showing green all the way up, any of those metals can react with steam. So these metals that can react with cold water, they definitely can react with steam as well. Okay, it's not just the green block, it's anything above the green block that can react with displacing hydrogen gas from steam. But if I'm in the yellow block here, not only can it react with steam, it can also react with cold water to release hydrogen gas. Now, if I have metals here from lead to cobalt listed, we're saying those react with acids, but guess what? Everything above that. So over here we see this blue block extending up to the top. Everything from lead all the way up to potassium can react with acids. We're just saying that cobalt, nickel, tin, and lead will not react with anything above it on the list. It won't react with steam, won't react with cold water, but anything above this point could react with acid, right? So every metal above the hydrogen on this list could react with acids. Every metal above cadmium on this list could react with steam. Every metal at sodium above could react with cold water. That's what we're saying here to cause a single displacement reaction. So I could say that cobalt could be reacted with hydrochloric acid. We would release hydrogen gas, and we end up with the metal chloride. So we end up with the acids anion with the metal, and we end up with cobalt 2 chloride forming and hydrogen gas being released. Now, if I had a metal below hydrogen on this list, those metals below will not react with acids usually. They will not react with steam, and they will not react with cold water. So I noticed that my antimony, bismuth, copper, silver, mercury, palladium, platinum, and gold all have such low reactivities. They do not want to oxidize to form cations readily. They tend to stay reduced and be neutral metals. And so if I try to predict some reactions here, I could say that zinc, since zinc is high enough on this list that it could react with steam or acid, if I add hydrochloric acid to zinc, we expect it to react in a single displacement process to produce zinc chloride and hydrogen gas. However, if I add hydrochloric acid to copper, we can see that when I add the hydrochloric acid to copper, that we expect there to be no significant reaction, because the hydrochloric acid will not cause hydrogen to be displaced when it's reacted with any of the metals in this lowest block on the metal activities table. Okay, so I can start to make those types of predictions. Now, something I want to ask you about is, since we saw aluminum reacting with iron, we know aluminum would rather be a cation than iron because it's above it on the list. Now, what if I had something like, let's say, silver metal and I tried to react that with rust, iron 3 oxide. What do we expect to have happen? Sorry, that should be a 2. Iron 3 oxide. So now the iron's a cation again. And we've seen that the iron cation can go to elemental iron depending on the metal that is performing a single displacement reaction. Now, if I look at this case, the aluminum was above iron. In this case, silver is down here far below iron, where iron is here. If we look at that scenario, since iron's above it on the list, iron would prefer to be the cation at the end of the reaction, and silver would prefer to be a neutral metal at the end of the reaction. And so if I have this situation, we expect that the silver won't end up forming a cation, it will not oxidize, it would rather stay reduced. And so the iron, which is already oxidized, has already lost electrons to form cations, tends to be stable as it is. So if I see a metal trying to perform a single displacement reaction with a compound that has a metal higher on the list, we expect no reaction to occur because we're already in the most stable states for these metals. The metal lowest on the list at the end of the process should stay in its metallic neutral form. The metal higher on the list should stay as a cation. And I already had those situations here with silver reacting with iron 3 oxide, so no reaction occurs, so I can just put an NR. I've been known on tests to give you situations where the metal reactivity series list, which you will have available on the test, will help predict no reactions might occur. So please realize I will check to see if you predict when reactions will or will not happen using the metal activity series list. So let's practice this for a couple more examples. Let's consider magnesium. Now magnesium will displace acid is what I'm asking. So if I look at it, magnesium is high enough on the list that it will not react with cold water to produce hydrogen gas, but it is high enough on the list that it could react with steam, and it's high enough on the list that it could also react with acids. So what I would predict then is that magnesium metal could displace protons from an acid. So let's say I have magnesium metal and hydrochloric acid. Since magnesium is high enough on the list, we can expect to form magnesium chloride. So the magnesium forms cations. Remember, higher on the list, we want to form cations to form a stable oxidized metal. And so I get magnesium chloride. And then since I'm high enough on that list, I end up with hydrogen gas being displaced. Okay, so the next question, so that was yes. So the next question is, will aluminum displace protons from acid? Definitely, it definitely will do that. If we look at aluminum reacting with an acid, it's high enough on the list that we expect acid to react with anything above it here. So aluminum will definitely react with an acid to displace hydrogen gas. The next we might ask, will iron react with an acid? Sure, it's still high enough on the list. We're still above hydrogen on the list, so all of these will react with acids to release hydrogen gas. Whoops. Now, will iron displace zinc? Let's consider that. So if iron is displacing zinc, we'll have iron metal reacting with zinc. And so I could have zinc, let's say nitrate. So there's zinc, nitrate. And if I want to consider if I have a solution of zinc nitrate that I put a piece of iron in, will it displace the zinc to form a product? Well, I look at which metal's higher on the list. The metal higher on the list should like to be at the end of the reaction a cation. The metal lower on the list would rather be metallic. So we tend to see that zinc is highest on the list. So we end up with the zinc metal would rather be a cation. The iron lower on the list would rather be metallic iron. So since we already have metallic iron, we already have the zinc cation, we say that there's no reaction. And so in that case, we'd say that there's no reaction there. Now, if we use the metal activity series list here to predict any reaction that might occur with calcium metal and water, let's think about what this means. Calcium metal will react with cold water. So I predict a reaction will happen that will produce hydrogen gas. So I go ahead and write calcium metal here, and that calcium metal then will react with water, and how I decide if it will react with cold water, and if I have cold water it's going to be in the liquid state, right, so room temperature. How I decide if it will react is if it's anywhere above sodium on this list, so where it says reacts with cold water to give hydrogen gas. So if it reacts with the cold water, I could end up with either forming calcium oxide, but remember calcium oxide and water will continue to react and will form calcium hydroxide. So I would accept either one of these as products on a test. Just realize the end product is going to be calcium hydroxide in water as it continues to react. And then I'll also form hydrogen gas being released. So the bubbles that we're seeing in the test tube in this picture, we put calcium metal in there. These bubbles are this hydrogen gas being produced. This is a single displacement reaction because we see the form of A, the calcium coming stag to the dance, reacting with B and C, where B is the hydrogen gas, ends up going home alone at the end of the dance, and we ended up with calcium dancing with C, which is the oxygen for the rest of the dance, or with hydroxide. So this is single displacement as well. The meta activity series list just helps us predict whether the reaction will occur or not. Okay, so that's the end of our first discussion on chemical reactions. We'll look at predicting solubility and precipitation reactions in our next discussion.